This is a story written in ancient light. A single image from the James Webb Space Telescope holds thousands of galaxies, each a smudge of fire from a time before Earth existed. You are looking at the universe's first chapters, captured by a machine that is not merely a telescope. It is our greatest time machine and most patient cosmic detective. By the end of this journey, you will understand how this one instrument is completely rewriting the story of our cosmos, from the spark of the earliest stars to the air of distant worlds. It has already found galaxies that should not exist and sniffed the chemistry of planets 1,000 light-years away. What do you believe is waiting for us in the dark? To achieve this, the telescope had to become something entirely new. The Hubble Space Telescope, our beloved eye in the sky for decades, sees primarily invisible light, the same rainbow our human eyes perceive. But to look back to the dawn of time, you need a different kind of vision. The universe is expanding, stretching the very fabric of space. As it stretches, the light traveling through it gets stretched too, its wavelengths pulled longer and longer, shifting from visible blue into the invisible infrared. The farther back you look, the more extreme this redshift becomes. The first starlight in the cosmos has been traveling for over 13.5 billion years. By the time it reaches us, it is not a visible sparkle. It is a faint, ancient warmth, a whisper in the infrared. Hubble could only hear the shouts. James Webb was built to listen for the whispers. But infrared light presents another challenge, one of cosmic dust. Nebulas where stars are born, the dense cores of galaxies, the shrouds around dying suns, all these are veiled in great clouds of dust that block visible light completely. To our eyes and to Hubble, these are dark voids, but dust glows with heat. It radiates in the infrared, so with its infrared eyes, James Webb does not see the dust as a wall. It sees the dust itself glowing, revealing the stellar nurseries and galactic hearts hidden within. This is its dual superpower. It sees the oldest, most redshifted light, and it sees through the cosmic fog that hides creation's most active workshops. This mission demanded a design unlike any before. While Hubble orbits close to Earth, James Webb had to journey 1,000,000 miles away to a gravitationally stable point called Lagrange Point 2. Here, it can shield itself with a sun shield the size of a tennis court, chilling its instruments to nearly 267 degrees below 0 Celsius. At that profound cold, the telescope's own heat doesn't drown out the faint infrared warmth from the distant universe. Every component, from its 21-foot segmented gold mirror to its exquisitely sensitive detectors, was engineered for one purpose: to collect that ancient warmth and translate it into a story we can see. It is not just a better telescope, it is a machine built to read a different language, the language of heat and time, written across the void. Building a machine to listen for the universe's whispers meant protecting it from any shout. On Christmas morning, 2021, the most complex and fragile observatory ever conceived sat folded like a technological origami inside the nose cone of an Ariane 5 rocket. Its destination was not orbit, but a point of perfect balance in space, 1,000,000 miles from Earth. For 29 minutes, the rocket performed flawlessly, but for the scientists and engineers watching, that was just the opening note of a symphony of anxiety. The real test began once the telescope was alone in the dark. Over the next 2 weeks, James Webb had to perform a high-stakes mechanical ballet with no chance for a second take. First, its massive sun shield, as large as a tennis court, had to unfurl. Picture 5 layers of a specialized plastic film, each thinner than a human hair, pulled taut by hundreds of pulleys and cables. A single tear, a snagged cable, and the mission would fail. This shield was the telescope's life support system, creating a permanent shadow so profound that the instruments behind it could cool to a mere 7 degrees above absolute zero. Only in that deep cold could its infrared sensors detect the faint heat of distant galaxies without being blinded by its own warmth. Once the shield was secure, the next act began. The telescope's iconic mirror, a 21-foot-wide honeycomb of gold-coated beryllium, was not one piece but 18 hexagonal segments. They had been folded to fit inside the rocket. Now, each one had to swing into place with nanometer precision, aligning themselves to act as a single, perfect eye. It was like assembling a massive, intricate puzzle in the vacuum of space, with robotic arms performing the task automatically, a million miles from any human hand. The collective sigh of relief when the final lock clicked into place was felt across continents. This journey ended at a special gravitational parking spot called Lagrange Point 2. Here, the combined pulls of Earth and the Sun create a stable point where the telescope can orbit the Sun in lockstep with our planet, always keeping its sun shield pointed toward the Sun, Earth, and Moon. It is a vantage point of perpetual shadow and perfect silence, the only place this ice-cold observatory could do its work. This was not just an American achievement. That gold-coated mirror was polished in Alabama. Its infrared sensors came from Canada, and the Ariane rocket that carried it so perfectly was a gift from Europe. It stands as a monument to decades of human ingenuity, a fragile piece of art we sent to a point of cosmic balance to ask the oldest questions. And after that harrowing unfurling, after the mirrors aligned and the systems woke in the deep cold, the telescope finally turned its golden eye to the void and took its first look. What it saw immediately began dismantling our cosmic textbooks. The first test images were more than a technical check, they were a revelation. Scientists pointed the telescope at a seemingly dark and empty patch of sky, a region Hubble had already observed in exquisite visible light detail. What came back was not a clearer version of the same picture. It was a completely different universe, where Hubble saw a handful of bright galaxies against a star speckled black. James Webb's infrared vision unveiled a tapestry. That same dark patch was now crowded with thousands of faint, reddish smudges, each one a galaxy so ancient its light had been stretched completely out of the visible spectrum. It was like lifting a veil we never knew was there. This is the power of seeing in infrared. Think of a foggy night. Your car's headlights shining visible light illuminate the fog itself, creating a blinding wall. But switch to fog lights which use a longer wavelength of light, and you can suddenly see through the mist to the road ahead. Cosmic dust acts the same way. Great clouds of it shroud the places where stars are born and hide the chaotic hearts of galaxies. To telescopes like Hubble, these are dark voids, but that dust, warmed by the young stars inside, glows with its own heat in the infrared. James Webb doesn't see the dust as a wall. It sees the wall glowing, revealing the stellar nurseries and violent cores hidden within. To detect that incredibly faint heat signature, the telescope itself must become colder than the void around it. Its instruments are chilled to a staggering -267 degrees Celsius, just 7 degrees above absolute zero, the point where all molecular motion stops. At that temperature, the telescope's own heat doesn't overwhelm the delicate infrared whispers from across the cosmos. It is an ice-cold machine listening for the warmth of creation. The comparison is undeniable. A Hubble image of the iconic pillars of creation shows majestic, dark towers of gas and dust silhouetted against a glowing nebula. It is beautiful, but it is a silhouette, a shadow. The James Webb image of that same region is a breathtaking invasion of privacy. Its infrared eyes peer straight through the dusty pillars, which now glow with an ethereal, rusty light, revealing hundreds of previously hidden newborn stars blazing within, their powerful stellar winds carving new shapes in the cosmic cloud. One telescope shows us the curtain, the other pulls it back to show the spectacular performance happening behind it. This fundamental shift in vision is why every new image is not just a photograph but a discovery. We are no longer just looking at the universe, we are seeing into its secret rooms. That first deep field image was not just a pretty picture, it was a declaration. The target was a region of space known as SMACS 0723, a massive cluster of galaxies about 4.6 billion light-years away. To previous telescopes, it was a noteworthy grouping. To the newly opened eye of James Webb, it became a window into infinity. This single image, assembled from just 12.5 hours of observation, is the deepest and sharpest infrared view of the distant universe humanity has ever captured. Every speck of light, every smear and arc is an entire galaxy. Thousands of them crowd the frame, a cosmic tapestry so dense it redefines our sense of scale. Among them are galaxies glowing with the reddish hue of extreme age, their light emitted when the universe was less than 1 billion years old. We are seeing them not as they are, but as they were, mere infants in cosmic terms. But the real magic of this image lies in its warped shapes. Look closely, and you will see galaxies stretched into long, faint arcs like smiles scratched into the darkness. This is not a flaw in the image, it is the universe bending light itself. The immense gravity of the foreground galaxy cluster acts as a natural magnifying glass, warping the fabric of space around it. Light from galaxies far behind the cluster follows this curved space, bending around the cluster on its way to us. This phenomenon, called gravitational lensing, magnifies and distorts those incredibly distant background galaxies, making visible objects that would otherwise be far too faint for even James Webb to see. It is as if the universe provided its own telescope, and James Webb is peering through its lens. So this image is a double revelation. First, it proves the telescope works with breathtaking precision, its golden mirror gathering ancient light exactly as designed. Second, and more profound, it shows us a cosmos far more crowded and active in its youth than we ever predicted. Those tiny red smudges are not just distant points of interest. They are entire cities of stars from the universe's first chapters, now visible because a machine 1 million miles away can feel their ancient warmth. This was the proof of concept. The time machine was working, but the real shock was about to come when we looked closer at those infant galaxies and realized our story of cosmic dawn was wrong. Those tiny red smudges held a secret that would shake astronomy to its core. As teams around the world analyzed the light from these earliest galaxies, a startling pattern emerged. These cosmic infants, seen as they were just 400 million years after the Big Bang, were not the faint, chaotic blobs theory had predicted. They were massive. They were bright, and many of them already showed the elegant disk and spiral structures we associate with mature galaxies like our own Milky Way. One of the most shocking examples is a galaxy now known as Glass Z13. We see it as it existed a mere 300 million years after the universe began. According to our best models, that is simply not enough time for gravity to pull together so much gas, forge so many stars, and organize them into such a coherent, luminous city. It is like finding a fully formed, articulate child in a nursery you just built yesterday. The discovery forced a profound and thrilling question: how did galaxies get so big so fast? Our previous timeline for cosmic dawn, the era when the first stars and galaxies ignited, appears to be off by a colossal margin. The universe seems to have gotten down to business with a speed and efficiency we never imagined. This is not just a small adjustment, it is a fundamental challenge to our understanding of structure formation in the early cosmos. For decades, the prevailing story said that after the Big Bang, the universe was a dark, expanding soup of hydrogen and helium gas. Tiny fluctuations, seeds imprinted by the Big Bang itself, slowly gathered more gas through gravity. Over hundreds of millions of years, these clumps grew, eventually becoming dense enough to collapse and spark the first stars. Those stars then gathered into small, irregular protogalaxies, which only later merged to form the grand spirals and ellipticals we see today. James Webb's data suggests this entire process was dramatically accelerated. The seeds for structure must have been much larger, or the early conditions far more fertile. for galaxies to achieve such size and order in what amounts to a cosmic blink. This mystery pulls us toward one of the greatest unknowns in physics: dark matter. We believe this invisible, mysterious substance forms the gravitational scaffolding of the universe. Ordinary matter, the stuff of stars and planets and us, simply falls into the wells created by dark matter. For galaxies to form this quickly, that dark matter scaffolding must have been in place and surprisingly robust almost immediately after the Big Bang. James Webb is not just showing us early galaxies, it is giving us our first real clues about the behavior of dark matter in the universe's first moments. Every unexpectedly bright, surprisingly structured galaxy is a piece of evidence in a new cosmic detective story. We are being forced to rewrite the opening chapters of our own existence, and the plot is turning out to be far more dramatic than we ever dreamed. This cosmic detective story does not only peer back in time, it also pulls back the curtains on the present. One of the most stunning examples is a place you may already know: the pillars of creation. Hubble's iconic visible light image is a masterpiece of cosmic silhouette. It shows three towering columns of cold gas and dust rising like ghostly spires against a backdrop of glowing stellar radiation. They are beautiful, dark, and mysterious, their shapes hinting at the violent stellar winds carving them, but they are fundamentally a curtain. The James Webb Space Telescope's mid-infrared view does not show us the curtain. It shows us the glowing fabric of the curtain itself and the spectacular activity happening behind it. In Webb's image, the familiar pillars are transformed. The opaque dust that appeared dark to Hubble now glows with a haunting, rust-colored light because the telescope is detecting the heat radiating from the dust grains themselves. This shift in vision is revolutionary. Suddenly, the pillars are not solid walls but complex, ethereal structures filled with wispy tendrils and cavernous hollows. And within that glowing dust, hundreds of tiny, bright red dots appear. Each one is a newborn star or a protostar still swaddled in its cocoon of gas and dust. Hubble could only infer their presence. Webb shows them to us directly, like fireflies trapped in amber. We can see the fierce jets of material blasting away from these infant stars, the powerful outflows that act like cosmic blowtorches, sculpting the surrounding nebula and ultimately determining which clumps of gas will collapse to form new stars and which will be blown apart. This level of detail turns a beautiful picture into a vital scientific document. Astronomers are not just admiring the view, they are taking a census. They can count the precise number of new stars, measure the energy of their outflows, and map the density and temperature of the gas around them in 3 dimensions. It is like having a front-row seat to the factory floor of star formation, watching the machinery of gravity and radiation at work in real time. By comparing these 2 images, we witness the fundamental difference between looking at the universe and seeing into it. One is a portrait of majestic obscurity. The other is an intimate, detailed blueprint of creation itself, revealing the violent and beautiful processes that build the worlds we someday hope to find. The story of a star is written in the dust around its birth and the ashes of its death. James Webb's infrared vision lets us follow this entire epic, from the first whispers of formation to the final echoes that seed new worlds. Around infant stars, the telescope sees not just the stars themselves, but the swirling, flattened disks of gas and dust that orbit them. These are protoplanetary disks, the raw material for future solar systems. Within these dusty rings, gravity begins to clump particles together, forming pebbles, then rocks, then planetary cores. Webb's instruments can analyze the composition of these disks, identifying the ices and silicates present, giving us a chemical blueprint of planets under construction. It is like watching a construction site and being able to list every type of brick and mortar being delivered. This changes our understanding of our own origins, showing us the common and chaotic processes that likely led to Earth. But for every stellar cradle, there is a cosmic graveyard. When a star like our Sun reaches the end of its life, it does not go quietly. It sheds its outer layers in a series of gentle pulses, creating a breathtakingly beautiful shroud of glowing gas called a planetary nebula. The Southern Ring Nebula, a favorite target, looks like a delicate, glowing hourglass in Hubble's visible light. James Webb's view is far more forensic. Its infrared eyes pierce through the outer shell of gas, revealing a second, previously hidden star orbiting at the nebula's heart. This discovery solved a long-standing mystery, showing the complex gravitational dance that sculpted the nebula's intricate shape. More importantly, Webb's spectrographs dissect the light from that glowing gas, identifying the specific chemical fingerprints within it. In that nebula, it finds the signatures of carbon, hydrogen, and oxygen, elements cooked in the star's core and now being blown back into interstellar space. For stars many times more massive than our Sun, the end is violently spectacular, a supernova explosion. The remnants of these blasts, like the famous Cassiopeia A, are chaotic webs of expanding debris glowing with the heat of the explosion's aftermath. Here, Webb's chemical analysis becomes truly profound. In these remnants, it detects the signatures of much heavier elements like silicon, sulfur, and even iron. This is the universe's ultimate forge. The incredible temperatures and pressures of a supernova are the only places where these complex atoms can be created. James Webb is effectively taking inventory of a stellar factory's output. Every element heavier than hydrogen and helium, from the calcium in your bones to the iron in your blood, was forged in the heart of a dying star and scattered across the galaxy by an explosion like this. The telescope's images of these graves are not just post-mortem portraits. They are chemical maps showing how the universe recycles star stuff, enriching the cosmic clouds that will one day collapse to form new stars, new planets, and potentially new life. We are not just observers of these cycles, we are products of them, made from atoms that once lived and died inside a star. The chemistry of a star's death becomes the potential for life elsewhere. This cosmic recycling leads us to the most profound question of all: are we alone? While the James Webb Space Telescope looks back in time to see our origins, it also looks outward with a new tool to answer that question by sniffing the air of distant worlds. For the first time, we are moving from simply finding exoplanets to truly understanding them, analyzing the very composition of their atmospheres light years away. The method is as elegant as it is powerful, and it relies on a cosmic eclipse. When a distant planet passes in front of its host star from our point of view, an event called a transit, a tiny fraction of the star's light filters through the planet's thin outer atmosphere. Different molecules in that alien air absorb specific colors or wavelengths of that starlight. By comparing the star's normal light to the light filtered through the atmosphere during a transit, Webb's exquisite spectrographs can detect which wavelengths are missing. Those missing pieces form a chemical barcode, a unique fingerprint revealing what that atmosphere is made of. It is not a photograph of the planet, it is a forensic analysis of its sky. One of Webb's first and most stunning targets was a world called WASP 96b, a searing hot gas giant larger than Jupiter orbiting perilously close to its sun. As the planet transited, Webb's instruments collected the filtered starlight and broke it into a spectrum, a rainbow of data. The graph that came back showed a clear, unmistakable dip at the precise wavelength absorbed by water vapor. It was a definitive detection, the kind of crisp data astronomers had dreamed of for decades, but the data held another surprise: evidence of clouds and haze. Previous observations had suggested this world had clear skies. Webb revealed a more complex and more realistic cloudy atmosphere. This single observation validated the entire technique. If we can detect water and clouds on a bloated, inhospitable gas giant 1,000 light-years away, then the path is open to study smaller, more temperate worlds. The ultimate goal is to apply this same method to rocky, Earth-sized planets orbiting within their star's habitable zone. that Goldilocks region where liquid water could exist on the surface. In those atmospheres, we will search for more than just water vapor. We will look for the chemical imprints of potential biosignatures, gases like oxygen, methane, and carbon dioxide in combinations that are difficult to explain without the presence of life. Webb is already turning its gaze to such promising systems, like the 7 rocky worlds orbiting the nearby star TRAPPIST-1. Analyzing their thin, rocky world atmospheres is a far greater challenge than studying a puffy gas giant, but it is the challenge this telescope was built for. Each transit, each tiny dip in starlight, is a whisper from another world carrying the story of its air, its climate, and perhaps its potential. We are no longer just planet hunters. We have become interstellar atmospheric scientists, learning to read the skies of other suns. That search for life leads us to a quiet, cool star just 40 light-years away. TRAPPIST-1 is not like our Sun. It is a red dwarf, smaller, cooler, and dimmer, a faint ember compared to our solar furnace. Yet around this modest star, astronomers found a treasure trove, not 1 but 7 rocky worlds, each roughly the size of Earth. 3 of these planets orbit within the star's theoretical habitable zone, the region where temperatures could allow for liquid water to pool on the surface. It is the most compact family of Earth-sized worlds we have ever found, a complete solar system in miniature, and it presents the James Webb Space Telescope with its most tantalizing and difficult challenge. The goal is to sniff the air of these distant cousins, but the planets are small, their atmospheres whisper thin, and the star they orbit is prone to violent temper tantrums in the form of powerful stellar flares. Red dwarfs are famously active, and a torrent of radiation could strip away a planet's atmosphere or bathe its surface in harmful ultraviolet light. Another quirk of orbiting so close to a dim star is tidal locking. Just as our moon always shows one face to Earth, these planets likely have a permanent day side and a permanent night side, creating extreme temperature contrasts that could make global climates wildly different from our own. All of these factors fuel a fierce scientific debate. Could a world like this, battered by flares and locked in a gravitational embrace, ever be a cradle for life, or are they all barren, airless rocks? James Webb is the only instrument we have that can provide answers. Its strategy is one of meticulous, repeated observation. The telescope must watch for the tiny, periodic dimming of the star as each planet transits. During those precious hours, it will collect the starlight that filters through any atmosphere, breaking that light into a spectrum. Scientists are not looking for a single molecule, but for a chemical story. They will search for the fingerprints of biosignature gases, combinations that hint at biological activity. Oxygen, especially in large amounts alongside methane, is a powerful signal, as on Earth it is continuously replenished by life. Carbon dioxide would tell us about the greenhouse effect and climate. The absence of an atmosphere would be a profound answer in itself, suggesting the star's fury has blown it all away. Every transit is a high-stakes experiment. The signals are incredibly faint, buried in noise, requiring Webb to observe dozens of transits for each planet to build up a clear chemical picture. It is a painstaking process of listening over and over for a whisper in a cosmic hurricane. The data now trickling in is the beginning of a new chapter. Early results for the innermost planets suggest they may be devoid of thick, puffy atmospheres, perhaps victims of their star's youthful rage. But the worlds farther out in the cooler habitable zone remain mysteries. With each observation, Webb is writing the first pages in the environmental history of another solar system. The answer it finds will reshape our understanding of what makes a world a home, and just how rare or how common a pale blue dot might be in the cosmos. Sniffing the air of a distant world is one thing, but what if you could see the world itself? For a select group of exoplanets, James Webb is doing just that, moving beyond transits to capture their actual light. These are not postcard pictures in the traditional sense. The planets are still just single, bright pixels, but within that single pixel is a universe of information. The challenge is staggering. A planet is billions of times fainter than its host star and orbits incredibly close to it from our distant vantage point. It is like trying to spot a firefly hovering inches from a brilliant searchlight from miles away. To accomplish this, Webb uses a sophisticated tool called a coronagraph, a tiny mask inside the telescope that physically blocks the overwhelming glare of the star itself. With the star's light suppressed, the faint glow of the orbiting planet can be isolated and studied. This direct light is a gold mine. By analyzing its spectrum, scientists can map the planet's temperature, detect clouds, and even trace global weather patterns. For a gas giant, they might find evidence of violent storms or jet streams circulating its atmosphere. This transforms a distant point of light into a dynamic, alien world with its own meteorology. The ultimate goal of this direct scrutiny and of the transit method is to search for the Holy Grail, a biosignature. A biosignature is not a single molecule, but a chemical story written in an atmosphere. It is a persistent, unexplained imbalance, a gas that should not be there in such abundance unless something is actively producing it. On Earth, our atmosphere is a glaring biosignature. It contains vast amounts of oxygen, a highly reactive gas that would quickly vanish if not continuously replenished by photosynthesis from plants and microbes. The simultaneous presence of methane, which oxygen should rapidly destroy, is another part of the story, hinting at constant biological production. Finding such a combination on a rocky exoplanet would be electrifying. But the cosmos is full of chemical tricks. An oxygen-rich atmosphere could also be forged by non-living processes, like the intense ultraviolet light from a star breaking apart water vapor and releasing the oxygen. Methane can be belched out by volcanic activity or produced by reactions between water and certain types of rock. A potential biosignature is not proof of life, it is a clue that demands investigation. This is where James Webb's profound power becomes essential. It does not just detect one or two gases. Its detailed spectra can reveal a whole suite of atmospheric components, the chemical context. Finding oxygen is interesting. Finding oxygen alongside water vapor, carbon dioxide, and the absence of certain destructive chemicals might make a stronger case. The telescope's ability to sense temperature and cloud cover adds more pieces to the puzzle, helping rule out geological explanations. Any future claim of discovered life will not rest on a single line in a spectrum. It will be built from a mountain of contradictory data, a comprehensive portrait of an alien environment that, against all other explanations, points toward biology. James Webb is gathering the first pages of that evidence, teaching us to read not just the words, but the entire grammar of an alien sky. The search for life on distant worlds begins with understanding our own home. While the James Webb Space Telescope peers across the galaxy, it has also turned its revolutionary gaze inward, conducting a grand tour of our own solar system with infrared eyes that see far more than visible light. Its images of Jupiter are not just portraits, they are dynamic weather maps. The giant planet's iconic bands swirl with unprecedented clarity, but Webb's vision goes deeper, capturing the faint glow of its high-altitude hazes and the brilliant blaze of its auroras at the poles. These are not the same as Earth's northern lights. They are generated by the planet's immense magnetic field interacting with particles from its volcanic moon Io, and Webb sees their structure in breathtaking new detail. Even Jupiter's delicate ring system, often overshadowed by Saturn's, is visible as a ghostly halo. For Saturn, the telescope's observations are helping solve a long-standing mystery, the length of its day. By mapping temperature variations and atmospheric patterns in the infrared, scientists are getting a clearer picture of the gas giant's deep internal rotation, something visible light cameras cannot penetrate. The ice giants Uranus and Neptune appear transformed. To our eyes, they are bland blue-green marbles. To Webb, they are vibrant worlds alive with meteorological activity. Uranus reveals its faint, dusty rings and a bright polar cap, while Neptune's image shows not just its familiar blue disk but also a series of bright, high-altitude methane ice clouds, and for the first time, a clear view of its entire ring system since the Voyager 2 flyby in 1989. Even Mars, a planet we have roved and mapped extensively, offers new secrets under Webb's infrared gaze. In a single observation, it can capture a global map of the planet's surface and atmosphere simultaneously, identifying the chemical fingerprints of carbon dioxide, carbon monoxide, and water vapor, and even detecting the glow of the planet's hot surface during a Martian day. This provides a synoptic, big-picture view that complements the ground-level work of our rovers. The tour extends to the frozen frontier. Webb has observed Pluto and its large moon Charon, not to see surface features in detail, but to analyze the composition of their ices like frozen nitrogen, methane, and carbon monoxide. This data is a time capsule revealing the conditions and materials present in the outer solar system during its formation over 4.5 billion years ago. It also studies other denizens of the Kuiper belt, that vast disk of icy remnants beyond Neptune. By measuring the reflectivity and chemical makeup of these primitive objects, Webb is helping us understand the original building blocks of the planets and the ancient environment from which our entire planetary system emerged. This local tour proves a profound point. The same tool that studies the universe's first galaxies is also the most powerful instrument we have for re-examining our own cosmic neighborhood, showing us that even the familiar holds stunning new secrets when seen in a new light. Mars glows. To the James Webb Space Telescope, our rusty neighbor is not just a distant point of light, but a source of intense, complex infrared radiation. Observing it is a unique technical challenge, a ballet of precision. The telescope was designed to detect the faintest whispers from the edge of time, not the brilliant shout from a planet next door. Mars is so close and so bright in infrared light that it can easily overwhelm Webb's exquisitely sensitive detectors. To avoid this, astronomers use very short exposure times and special observing modes, measuring only specific slivers of light. It is like using a microscope designed to study cells to examine a brightly lit rock, requiring careful adjustments to see the details without being blinded. The payoff is a revolutionary new kind of map. Webb's powerful spectrometer doesn't just take a picture, it scans the entire Martian disk, breaking its infrared glow into millions of individual spectra. Each tiny pixel in that scan contains the chemical fingerprints of whatever the light touched. From a million miles away, the telescope can create a global weather map and a surface composition survey in a single observation. It clearly detects the dominant blanket of carbon dioxide in the atmosphere, but it also picks up the fainter signature of carbon monoxide, a trace gas that tells a story of atmospheric chemistry and loss. Most tantalizing is its ability to map the distribution of water vapor and ice, seeing where water concentrates in the atmosphere and how it moves with the planet's winds and seasons provides a system-wide context that no single ground mission can achieve. This global view is the perfect complement to our robotic explorers on the surface. Rovers like Perseverance give us an intimate ground truth view, a close-up of the rocks and soil. But they are, by necessity, fixed to one location, experiencing one local weather pattern. Webb acts as the orbital companion, seeing the whole planet at once. It can watch a regional dust storm form and track its movement across thousands of miles, providing context for why the sky might darken at a rover's location days later. It can monitor the seasonal ebb and flow of polar ice caps and atmospheric gases, helping scientists build a more complete model of the Martian climate. This big-picture data is crucial for solving one of Mars's greatest mysteries, the history of its water. billions of years ago, Mars was a wet world with rivers and lakes. Today, it is a frozen desert. The question is, where did all that water go? Some is locked in polar ice and subsurface glaciers, but a significant amount was likely lost to space, stripped away as the planet's protective magnetic field faded and its atmosphere thinned. By measuring the ratios of different gases in the current atmosphere, particularly the isotopes of hydrogen locked in water vapor, Webb provides clues to the rate and timing of this ancient escape. It is reading the subtle traces left in the modern air to reconstruct a cataclysm that unfolded over eons. From a single set of observations, Webb delivers a planetary health report, a weather forecast, and a historical document. This ability to study our own solar system with the same instrument that observes the first galaxies is a stunning demonstration of its versatility, proving that the most powerful time machine ever built is also an unparalleled tool for understanding the world right next door. The chemistry of Mars is a local clue to a universal mystery. Across the cosmos, the James Webb Space Telescope is acting as a master chemist, decoding the molecular signatures written in the light from clouds of gas and dust. This is not astronomy in the traditional sense, it is cosmic forensics. The telescope's spectrometers work by capturing light and stretching it out into a detailed rainbow, a spectrum. Within that spectrum are dark lines and bright bands, each one a unique barcode corresponding to a specific molecule vibrating or rotating in space. By reading these barcodes, Webb can identify not just the presence of water or carbon monoxide, but astonishingly complex organic molecules, the very building blocks of life floating in the void. It finds these compounds in the coldest, darkest places, within the frigid molecular clouds where new stars are born. In one such cloud, Chameleon 1, located over 600 light-years away, Webb's infrared gaze did not just find simple ices. It identified the clear spectral fingerprints of frozen carbon dioxide, ammonia, and methane, but also more complex molecules like carbonyl sulfide. Most remarkably, it found evidence of molecules as intricate as benzene, a ring of 6 carbon atoms, and even tentative signs of ethanol, that is, alcohol, drifting in deep space. These are not signs of life, they are signs of life's potential. They are the prebiotic ingredients, the carbon-rich Lego bricks that existed in the cloud that formed our own solar system 4.5 billion years ago. The telescope sees them now being incorporated directly into infant solar systems. In the protoplanetary disks swirling around young stars, those same organic molecules freeze onto tiny dust grains. These icy grains stick together, forming pebbles and then planetesimals, the seeds of future planets. When those planetesimals collide to form worlds, they deliver a payload of water and complex organics. Webb has watched this delivery process in action, detecting water ice and a suite of organic compounds in the disks around stars like HL Tauri. This means the raw materials for oceans and for the chemistry that leads to biology are not rare accidents. They are a standard part of the planetary construction kit shipped to new worlds as they form. The profound implication is that our solar system was not uniquely blessed. The galaxy appears to be a vast organic factory, routinely manufacturing and distributing the essential components for life. Wherever rocky planets coalesce within the habitable zone of a stable star, they likely arrive pre-loaded with water and a rich inventory of carbon-based molecules. Webb is providing the observational proof for this staggering idea. The universe seems hardwired for chemistry that leads to complexity. Finding benzene in a distant cloud is more than a technical achievement, it is a philosophical revelation. It suggests that the path from stardust to a living cell, while still miraculous, may be a far more common road than we ever dared to hope. That cosmic factory of organic molecules operates within a hidden framework. The universe's grand structure, its vast web of galaxies and the emptiness between them, is not built from the atoms we see. It is sculpted by two profound and invisible forces, dark matter and dark energy, the greatest mysteries in modern cosmology. The James Webb Space Telescope cannot see these shadows directly, but it is providing the sharpest map yet of their influence, turning their abstract mysteries into measurable puzzles. Think of dark matter as the cosmic skeleton. We know it exists because we can see its gravitational pull. Galaxies rotate far too quickly for the amount of visible stars and gas they contain. They should fly apart, but something unseen, a massive halo of dark matter, holds them together with its gravity. Similarly, when we see the light from distant galaxies warped into arcs by the gravity of a foreground cluster, as in Webb's deep field images, most of that lensing power comes not from the visible galaxies, but from the immense, invisible cloud of dark matter enveloping the entire cluster. Webb's unprecedented depth and sharpness are turning these gravitational lenses into precision tools. By meticulously measuring how the images of thousands of background galaxies are distorted, astronomers can now map the distribution of the cluster's dark matter in 3 dimensions with finer detail than ever before. They are essentially creating an X-ray image of the cosmic skeleton, revealing how its invisible strands connect and shape the luminous galaxies we see. This data is already challenging models. The way dark matter seems to clump in the earliest universe, as suggested by those surprisingly mature infant galaxies, may force us to reconsider the very properties of this mysterious substance. Is it colder or more interactive than our theories assumed? Webb's observations are the new benchmark, the data against which all future ideas must be tested. If dark matter is the skeleton holding the cosmos together, dark energy is the mysterious breath pushing it apart. In the late 1990s, astronomers made a shocking discovery. The expansion of the universe is not slowing down due to gravity, as everyone expected. It is accelerating. Some unknown repulsive force, dubbed dark energy, appears to be dominating the cosmos, driving galaxies apart at an ever-increasing rate. Understanding dark energy means measuring the expansion rate, the Hubble constant, with extreme precision across cosmic time. This is where Webb's time travel capabilities become essential. By observing the most distant supernova, the standard candles used to measure cosmic distances, in pristine infrared clarity, it can refine our view of the universe's expansion in its youth. Even more powerfully, by studying the detailed structure of the early universe imprinted on the distribution of those first galaxies, Webb provides an independent check on our models of cosmic evolution. The critical question is whether the strength of dark energy has changed over time. Was it always a constant force, or has it evolved? By comparing the expansion rate 13 billion years ago, measured by Webb's ancient galaxies, to the rate measured in the more recent universe by other telescopes, scientists hope to see the fingerprint of dark energy's nature in the subtle differences. Is it the steady cosmological constant Einstein once imagined, or something far stranger and more dynamic? Webb offers our first clear look at the early chapters of this expansion story, providing the data we need to see if the plot has twisted. We stand at a remarkable point in our understanding. The James Webb Space Telescope is not going to announce the solution to dark matter or dark energy next week. These are puzzles that may take generations to solve. Instead, Webb is doing something equally vital. It is removing the fog of poor data. For decades, cosmologists have built elegant theories on a foundation of faint, blurry observations from the distant universe. Now they have a microscope pointed at cosmic dawn. Every unexpectedly massive galaxy, every exquisitely mapped gravitational lens, every precisely measured distance to an ancient supernova is a hard, undeniable fact. These facts are the anvil upon which our most beautiful theories will be forged or broken. The telescope is providing the deepest, sharpest ledger of the cosmos ever compiled, and we are just beginning to audit the books, searching for the entries written in invisible ink by the universe's dominant but unseen forces. The universe's deepest ledger arrives not in a bound book but as a torrent of ones and zeros. Every single day, from its lonely outpost a million miles away, the James Webb Space Telescope transmits back to Earth roughly 58 gigabytes of raw data, enough to fill a high-capacity laptop every 24 hours. Over a year, that builds into tens of terabytes, a fire hose of cosmic information that never turns off. This is the operational heartbeat of the mission, a global, human-powered engine of discovery that transforms those digital streams into the revolutionary images and spectra we see. Before a single photon is collected, the process begins with a fierce and democratic competition. Thousands of scientists from around the world submit detailed proposals, arguing for why Webb should point at their chosen patch of sky, for how long and with which instruments. Only the most compelling ideas, about 1 in every 7, are selected. This system ensures the telescope's precious time is spent on the questions that matter most to the scientific community, from studying the atmospheres of distant exoplanets to probing the very first galaxies. Once an observation is scheduled and executed, the data deluge hits the ground. Raw telescope data is not a finished photograph. It is a complex, encoded set of measurements that must be painstakingly processed, calibrated, and cleaned. Specialized pipelines run by the Space Telescope Science Institute remove instrumental artifacts, correct for known issues, and translate the numbers into calibrated images and spectra that scientists can trust. This is where the first magic happens, and it happens fast. For many observations, especially those in high-demand areas like the early universe or exoplanet transits, the processed data is released to the world immediately, with no exclusive period for the original team. This policy, called immediate public release, is a radical shift. It means that within hours of Webb observing a distant galaxy, that data is available online for any astronomer on the planet to download and analyze. This has led to a thrilling, crowdsourced race to discovery. A team in Europe might spot a strange chemical signature in an exoplanet's atmosphere at the same moment a graduate student in California notices an oddly shaped galaxy in the background of the same image. The result is a scientific discourse that moves at the speed of light, with papers sometimes published online within days of an observation, their findings debated and built upon by a global brain trust in real time. But the democratization goes even further. Every single piece of Webb's data, after an initial proprietary period for some programs, eventually flows into a permanent public archive. This archive is a treasure trove waiting for fresh eyes. Amateur astronomers, data-savvy citizen scientists, and researchers in countries without massive telescope budgets can all access the same raw cosmic material as the largest institutions. They can apply new analytical techniques, comb through data for overlooked details, or simply explore the cosmos from their own computer. This is perhaps one of Webb's most profound legacies. It is not just a tool for a select few, but a gift of cosmic perspective to all of humanity. The telescope itself is a silent, golden eye in the void, but the story it tells is written by a worldwide chorus of curious minds, each sifting through the starlight for a new truth. The greatest discoveries often begin with a single, stubborn piece of data that refuses to fit. For all our meticulous planning, the James Webb Space Telescope's most profound gift may be its ability to break our models, to show us where our cosmic story is wrong. This is not a bug in the science, it is the feature. Every anomaly is a signpost pointing toward a deeper truth we have yet to imagine. Already, Webb has delivered a cascade of these delightful surprises, each one forcing astronomers back to the drawing board. Take those impossibly early galaxies. Finding massive, structured cities of stars a mere 300 million years after the Big Bang is like finding a skyscraper in the middle of a freshly plowed field. Our theories of cosmic structure formation simply did not allow for such rapid, efficient construction. The universe, it seems, got its act together with breathtaking speed, and we are now scrambling to understand how. Perhaps dark matter behaved differently in that primeval heat, clumping faster than we thought. Or maybe the first stars were unimaginably gigantic, forging elements and dying in supernova that seeded subsequent generations with stunning haste. These galaxies are not just objects, they are urgent telegrams from cosmic dawn, demanding we rewrite the opening chapter. Then there are the chemical puzzles in the skies of other worlds. Webb's first detailed look at the atmosphere of exoplanet WASP 39b, a hot Saturn, revealed a surprise cocktail. Alongside the expected water vapor, it found a clear, strong signature of sulfur dioxide. This molecule, which on Earth comes from volcanic eruptions, is evidence of complex photochemistry happening in that alien air. The star's light is actively breaking apart other molecules, allowing new compounds to form high in the atmosphere. We did not just find a static blanket of gas, we witnessed a dynamic, alien weather system driven by chemistry. On another world, the gas giant K218b, Webb detected tantalizing hints of dimethyl sulfide in its atmosphere. On Earth, this molecule is only produced by life, specifically by marine phytoplankton. The detection is not yet confirmed, and non-biological processes are still possible, but its mere suggestion in the data sends a thrill through the scientific community. It is a whisper of the ultimate anomaly, a biosignature, reminding us that the biggest surprise of all may still be waiting in the data stream. Even in the beautiful death shrouds of stars, Webb finds the bizarre. In the Southern Ring Nebula, its infrared vision revealed the nebula's delicate structure was sculpted by not one, but two stars locked in a tight dance at its heart. This solved a decades-old mystery, but in other nebulae, like the stunning detail of the Cartwheel Galaxy, Webb reveals structures within structures, delicate filaments and bubbles within the chaos that current models of stellar winds and explosions cannot fully explain. Each unexpected filament is a clue to the precise physics of a star's final act. These surprises are the engine of science. A textbook universe would be a boring one and a closed book. A universe that constantly throws us curveballs, that presents us with galaxies too big and chemistry too strange, is a universe that is alive with mystery, inviting us to keep looking, to keep questioning. The James Webb Space Telescope is not just confirming what we already suspected. It is expertly, beautifully proving how much we have left to learn, turning every assumption into a question and every anomaly into the beginning of a new story. That river of cosmic data flows back to Earth through a network of human ingenuity, but the legacy of the James Webb Space Telescope is not written only in distant starlight. Its true impact resonates much closer to home, in the quiet hum of a hospital MRI machine and the precise beam of a laser reshaping a patient's cornea. Building an observatory of such staggering complexity demanded breakthroughs that refused to stay in space. They are already spinning off into our daily lives, turning the challenge of seeing the first galaxies into tangible benefits for medicine, manufacturing, and technology here on Earth. Consider the telescope's ability to stare at a single star while blocking out the blinding light of its neighbors, a task accomplished in part by a remarkable device called a microshutter array. This is a grid of over 250,000 tiny shutters, each the width of a human hair, that can be opened or closed individually to allow light from specific cosmic targets to pass through to the detectors while blocking everything else. Developing these microscopic, reliable shutters required pioneering new techniques in micro-electromechanical systems, or MEMS. This same ultra-precise, miniaturized control technology is now finding direct application in advanced medical imaging. Researchers are exploring how similar microshutter arrays could be used in new generations of MRI and CT scanners, potentially allowing for more targeted imaging with lower radiation doses, or enabling faster, higher-resolution scans that give doctors a clearer window into the human body. The quest for perfect vision in space is also refining vision correction on Earth. To function as a single, perfect eye, Webb's 18 mirror segments had to be aligned with nanometer precision, a fraction of the wavelength of light. The team developed incredibly sophisticated wavefront sensing and control algorithms to measure and correct the tiniest imperfections in the mirror's shape. This technology, designed to tune a telescope a million miles away, shares a fundamental principle with the lasers used in LASIK and other refractive eye surgeries. In both cases, a wavefront sensor meticulously maps the imperfections in an optical system, whether it's a cosmic mirror or the human cornea, and a controlled beam of light then reshapes the surface to achieve perfect focus. The algorithms refined for Webb are pushing the boundaries of precision in ophthalmology, leading to even more accurate and personalized laser vision correction procedures. Even the telescope's magnificent golden mirror is a testament to spin-off innovation. Creating those 18 ultra-lightweight, yet perfectly shaped beryllium segments required revolutionary manufacturing techniques. The processes developed for grinding, polishing, and coating these mirrors to atom-level smoothness have directly advanced the field of ultra-precise optics. This expertise is now being applied to improve the lenses in everything from semiconductor manufacturing equipment, which prints the tiny circuits on computer chips, to the next generation of Earth-observing satellites that monitor climate change and agricultural health. The telescope, therefore, is far more than a scientific instrument. It is a powerful engine of terrestrial innovation. The problems solved to peer into the cosmic dawn did not vanish once the rocket cleared the launch pad. They became a new toolkit, a set of solutions looking for earthly problems. This is the often unseen return on investment for grand scientific endeavors. We reach for the stars not just to understand our place in the cosmos, but to sharpen our tools, heal our bodies, and build a better world. The same relentless pursuit of perfection that lets us detect water vapor on a planet 1,000 light-years away is quietly at work, improving the clarity of a surgeon's view and the precision of the devices that connect our modern lives. These revelations are not confined to scientific journals. They spill out into our collective imagination, transforming from data into dreams. The James Webb Space Telescope's most immediate gift to humanity may be its breathtaking palette of color, a visual symphony that has reignited a global sense of cosmic wonder. Each image that flashes across our screens is a translation, a masterpiece of scientific artistry. The telescope sees in infrared light wavelengths invisible to our eyes. To create the visuals we see, specialists assign visible colors to different infrared channels, often using blue for shorter, hotter wavelengths and red for longer, cooler ones. This process, called color mapping, is not fabrication. It is interpretation, revealing structure, composition, and energy in a language our senses can understand. The result is a gallery of ethereal nebulae that look less like clouds and more like neural networks or vast watercolor paintings, and ancient galaxies rendered in hues of gold and crimson that feel both alien and deeply familiar. These are not just pictures, they are portals. They have instantly become part of our shared cultural fabric, inspiring musicians to compose ambient soundscapes based on the data, visual artists to reinterpret the cosmic vistas in paint and light, and poets to find new metaphors for infinity. Official collaborations have seen Webb's data turned into sheet music, where the brightness and position of stars dictate notes and rhythms, and into immersive digital art installations that allow people to step inside a nebula. This phenomenon taps into something primal. In a time often fractured by division, these images arrive as a unifying shock of beauty. They are a silent, stunning reminder that we all, every single one of us, live under the same cosmic ceiling. They fulfill a deep human need not just for knowledge, but for awe, for a perspective that momentarily lifts us above our terrestrial concerns and connects us to a story billions of years in the making. The telescope, in this light, becomes more than a machine. It is a global symbol of pure, shared curiosity. It asks no allegiance but to wonder, offering a humbling and magnificent mirror in which we see not just the birth of stars, but the enduring human desire to look up and ask what else is out there. This artistic legacy ensures the mission's impact will resonate far beyond any single scientific paper, weaving the cosmos directly into the tapestry of our culture. That shared sense of awe finds its most vital expression not in a gallery, but in a classroom. The James Webb Space Telescope has ignited a firestorm of curiosity in the minds of the next generation, becoming an unparalleled teaching tool and a beacon for future scientists. Across the globe, students are not just reading about discoveries in textbooks, they are watching them happen live. A teacher can pull up a news feed and show a brand new image of a stellar nursery, released just hours earlier, and say, "Look, this is what humanity saw for the first time this morning." That immediacy transforms astronomy from a historical subject into a living, breathing adventure. It makes the scientific process tangible, showing that discovery is not a list of facts from the past, but an ongoing, collaborative detective story where the next clue could arrive any day. Programs like the James Webb Space Telescope's own educational initiatives actively bridge this gap. They provide curated data sets, classroom activities, and visualizations tailored for different age groups, allowing a middle school student to measure the temperature of an exoplanet or a high school class to analyze the light spectrum of a distant galaxy using the same principles as professional astronomers. This direct engagement demystifies the process, showing that science is not magic performed by geniuses in lab coats, but a methodical craft anyone can learn. The inspiration reaches its peak with initiatives that hand the keys to the kingdom to students themselves. Through competitive programs like the Director's Discretionary Early Release Science, or through university partnerships, teams of undergraduate and even graduate students have been granted precious observing time on the telescope. Imagine being 20 years old and writing a proposal so compelling that you are given command of humanity's most powerful time machine for a few hours, to answer a question no one has ever asked before. These students learn to work with real, complex data, facing the same challenges and exhilarating breakthroughs as seasoned researchers. They are not just learning about science, they are doing it, contributing to the global archive of knowledge from their dorm rooms and campus labs. This early, hands-on experience is career-defining. The young engineer who studies Webb's deployment might one day design the even larger, more complex mirror for its successor. The student who writes code to analyze exoplanet atmospheres today could be the lead scientist interpreting the first confirmed biosignature a decade from now. The telescope is not just a machine for discovery, it is a talent incubator. By captivating young minds with the sheer beauty and mystery of the cosmos, it plants seeds of passion that grow into the expertise we will desperately need for the next great leap. The children who today gasp at a picture of the Carina Nebula on a classroom screen are the very people who will need to solve the monumental technical and ethical challenges of interstellar probes, lunar bases, and perhaps even first contact. Webb's greatest legacy, therefore, may not be a specific discovery about dark energy or an exoplanet. Its enduring gift could be the generation it inspires, a wave of thinkers who look at the universe not with complacency, but with the burning conviction that there is always more to find and that they are the ones destined to find it. Even the most powerful time machine has its horizon. The James Webb Space Telescope is a masterpiece of engineering, but it is not a perpetual eye on the cosmos. Its story has a final chapter already written in the cold mathematics of orbital mechanics. The telescope's life is measured in fuel. Nestled 1,000,000 miles away at Lagrange point 2, it is not in a perfectly stable orbit. Tiny gravitational tugs from the Sun, Earth, and Moon slowly pull it off station. To counteract this drift and keep its sunshield perfectly aligned, Webb must fire its small thrusters periodically, burning through a finite supply of hydrazine and dinitrogen tetroxide propellant. Meticulous planning and a flawless launch by the Ariane 5 rocket gifted the observatory extra fuel, extending its initial 10-year mission estimate. Yet the countdown continues. Every minor correction is a sip from a cup that cannot be refilled. One day, likely in the 2030s or beyond, the fuel will run out. Webb will no longer hold its precise position. Its sunshield will drift, its instruments will warm, and its unparalleled infrared vision will fade to black. It will become a silent, golden monument orbiting the sun, a relic of a golden age of discovery. This finite lifespan imbues every observation with urgency, a reminder that this window into the deepest universe is precious and temporary. Its vision, while revolutionary, is also specific. You cannot point this telescope just anywhere. Its greatest vulnerability is also its reason for being, that massive sunshield. To keep its instruments at nearly absolute zero, the shield must permanently block the light and heat from the sun, Earth, and Moon. This means Webb can only look at targets that are in the sky opposite this bright trio. A full third of the heavens, including the inner solar system, is forever off-limits. We will never get a James Webb close-up of Venus or Mercury. Their orbits keep them too near the sun from our perspective, placing them squarely in the forbidden zone behind the sunshield. Its design also trades one kind of sight for another. While it is peerless in the infrared, it is blind to most ultraviolet and high-energy X-ray light. These shorter wavelengths are crucial for studying the hottest, most violent phenomena in the universe, like the material screaming into a black hole or the furious hearts of quasars. For that, we still rely on observatories like the Chandra X-ray Observatory and the Hubble Space Telescope, which retains its sharp vision in ultraviolet and visible light. This is the fundamental truth of modern astronomy. No single telescope can tell the whole story. The universe communicates across the entire electromagnetic spectrum, from long radio waves to incredibly short gamma rays. Each band of light reveals a different chapter. Radio telescopes like the Atacama Large Millimeter Array see the cold dust and gas of stellar nurseries. Hubble shows us the visible beauty of galaxies and nebulae. Chandra captures the searing X-ray glow of million-degree gas. James Webb, with its infrared eyes, peers through dust and back to the first light. A complete understanding requires a cosmic chorus, not a solo. When Webb detects a surprisingly massive early galaxy, astronomers immediately turn to Hubble and ground-based telescopes to check its properties in visible light. When it finds complex chemistry in an exoplanet's atmosphere, theorists use data from other wavelengths to model the host star's radiation and its effects. Webb's greatest power is not in replacing other observatories, but in collaborating with them. Its data is the missing piece in a puzzle we have been assembling for decades, providing the infrared depth that makes the full picture snap into shocking, beautiful focus. Its limitations, therefore, are not failures. They are the edges of its masterpiece, defining what it alone can do and reminding us that discovery is always a collective human endeavor, built one wavelength at a time. The fuel gauge is not the only clock ticking. Every moment of observing time on the James Webb Space Telescope is a precious commodity, already allocated years into the future through a rigorous selection process. This planned cycle of observations is a roadmap to the next tier of cosmic mysteries, a schedule of deliberate stares into the dark that will define the next decade of discovery. The telescope's golden eye will return to iconic landscapes with even deeper vision. Nebulae like the pillars of creation will be studied not just for their beauty, but with spectroscopic tools that can map the velocity and temperature of gas in 3 dimensions, watching stellar winds carve the cloud in real time, as if observing weather patterns on a cosmic scale. The monitoring of exoplanet atmospheres will shift from initial detections to long-term climate studies. For promising worlds like those in the TRAPPIST-1 system, Webb will observe dozens of transits for each planet, building up a robust chemical profile to distinguish between a hazy, Venus-like hellscape and a clearer, more temperate sky. It will also target smaller, rocky worlds around quieter stars, expanding our catalogue of potentially habitable environments beyond a single, famous system. New deep field surveys will point the telescope at different patches of cosmic emptiness, building a statistical census of the early universe. Is the abundance of those surprisingly mature infant galaxies a universal rule, or did we just get lucky with our first look? Only by surveying multiple deep fields can we know for sure, mapping the large-scale structure of the cosmos in its first billion years. And Webb will turn its infrared gaze to the most violent engines in the universe, the supermassive black holes at the hearts of galaxies and the brilliant quasars they power when feasting. By studying the dust and gas swirling into these gravitational monsters, the telescope can trace the growth of black holes in the early universe and understand their profound influence on galaxy formation. Each planned observation is a direct assault on a fundamental question. What exactly are the earliest galaxies? Are they truly as massive and structured as they appear, or does their light tell a more complex story of unimaginably bright populating stars? Webb's detailed spectra will weigh them, date them, and take their chemical temperature. Do any exoplanets show definitive signs of habitability? The search moves beyond detecting water vapor to seeking chemical disequilibrium, that suggestive cocktail of gases that might point toward an active biosphere. And what is the true diversity of planetary systems? We have found hot Jupiters, super-Earths, and mini-Neptunes. Webb will study the atmospheres of these alien worlds across the full spectrum, revealing whether our own solar system's architecture is a common blueprint or a cosmic oddity. The road ahead is lit by specific targets, but its destination is the unknown. Every answer Webb provides will inevitably lead to two more profound questions, pulling us deeper into the story of where we came from and who or what else might be out there staring back. Even as Webb writes its story in starlight, the next chapters are already being sketched on engineers' drawing boards. The James Webb Space Telescope was a monumental gamble that paid off, and its success is not a finale but a blueprint. It has proven that we can build and operate revolutionary observatories at a point of perfect gravitational balance a million miles away. It has refined the technologies of segmented mirrors and ultra-cold infrared sensors to an art form. Most importantly, it has defined the urgent questions we must answer next. The mission's greatest legacy may be the clear path it has illuminated for its successors. One concept now moving from dream to concrete study is NAS, a proposed habitable worlds observatory. Imagine a telescope designed with a single, breathtaking goal: to directly photograph an Earth-like planet orbiting a Sun-like star and analyze its atmosphere for signs of life. This is not a general-purpose observatory like Webb or Hubble. It is a hunter built for one specific prize. The technical leap is staggering. An Earth twin would be 10 billion times fainter than its host star and located extraordinarily close to it in the sky, like trying to discern a speck of dust glowing next to a lighthouse beam from across an ocean. To achieve this, the Habitable Worlds Observatory would need a mirror even larger than Webb's, perhaps 30 feet across, and an advanced internal coronagraph, a device of unprecedented complexity to block the star's glare with near-perfect precision. It would operate at Lagrange Point 2, building directly on the orbital expertise Webb has provided. This telescope would not just find planets, it would study them in a way Webb cannot, taking their family portrait and reading the chemistry of their air in search of that ultimate signature. While such a space-based visionary is being planned, the ground is also rising to meet the sky. In the high deserts of Chile, construction is underway on the extremely large telescope. When completed later this decade, its main mirror will be an astonishing 130 feet wide, a mosaic of nearly 800 individual segments, gathering more light than all of the existing large optical telescopes combined. Perched under Earth's protective but blurring atmosphere, it will use adaptive optics, a system of lasers and deformable mirrors that correct for atmospheric turbulence in real time, to achieve a clarity rivaling space telescopes for certain observations. The extremely large telescope will peer into the hearts of galaxies, watch planets form in disks around young stars, and conduct its own detailed studies of exoplanet atmospheres, creating a powerful ground-based partner to the space observatories. These future instruments represent a shift in strategy. Webb is a peerless generalist, a time machine, a chemist, and a cartographer all in one. Its successors are being designed as specialists armed with the knowledge Webb provided. The Habitable Worlds Observatory exists because Webb is currently proving that we can analyze exoplanet atmospheres, showing us what to look for and how hard it will be to find it on a smaller, rocky world. The need for giant ground-based telescopes is underscored by Webb's own discoveries of puzzling early galaxies, objects we will want to study with every tool at our disposal, from the radio waves to the X-rays. James Webb, therefore, is the pioneering pathfinder. It is the scout that climbed the tallest hill, radioing back maps of a breathtaking new landscape and pointing to the most promising valleys to explore next. Its finite fuel and specific vision are not limitations but a passing of the torch. Every stunning image, every chemical barcode from a distant world, every ancient galaxy that breaks our models is more than a discovery. It is a question shouted back to Earth, a challenge to the next generation of engineers and scientists. The telescope's golden mirror does not just collect light from the past, it illuminates the road ahead. The true legacy of the James Webb Space Telescope is not found in any single discovery. It is woven into the fabric of a new cosmic perspective, a fundamental shift in how we see our place in the story. For centuries, we have told ourselves a particular tale of the universe, one of gradual, predictable evolution from simple beginnings. The first galaxies were faint, chaotic seeds. Planets took eons to coalesce, and life, if it existed at all, was a rare and fragile accident. In just a few short years, Webb has gently but firmly taken that old narrative, held it up to the light, and revealed it to be a comforting fiction. The universe it shows us is not slow and orderly. It is dynamic, complex, and startlingly efficient, bursting with potential from the very first moments. Those infant galaxies, massive and structured, tell us the cosmos got off to a running start, building its grand architecture with a speed we never anticipated. The chemical barcodes from stellar nurseries and planetary atmospheres reveal a galaxy that is not a barren void, but a vast organic factory, pre-loading new worlds with the very ingredients for oceans and the chemistry of life as a standard part of the assembly process. This is a universe that seems hardwired for complexity. The distance between a swirling cloud of benzene in deep space and the building blocks of a cell feels less like an impossible chasm and more like a series of steps on a well-trodden path. Webb is shrinking time and space in a profound way. It connects the dots between the carbon forged in a dying star, the delivery of that carbon to a young planet, and the potential for that planet to develop an atmosphere we can now sniff from a million light-years away. The gap between the first starlight and our own sun feels smaller. The alien worlds of the TRAPPIST-1 system are no longer just points of light, but tangible places with weather, chemistry, and history we are beginning to read. This new perspective is both humbling and electrifying. It humbles us because it reveals how much of the story we have missed, how our models were simplifications of a far richer reality. Yet it excites us because it paints a cosmos of breathtaking creativity, where the conditions for life appear to be not a miracle but a common feature. We are not lonely observers in a silent, static universe. We are participants in an ancient, ongoing, and astonishingly fertile drama, one that began with a burst of light and continues to unfold in the hidden chemistry of distant skies. Webb's golden mirror does more than collect photons. It reflects back a universe that is more alive, more interconnected, and more wondrous than we ever dared to believe. The story told by this golden eye is one of profound revolutions. It has rewritten cosmic history by revealing the shocking maturity of the first galaxies, proving the universe built its grand structures with breathtaking speed. It has chronicled the intimate life cycles of stars, from their hidden birth within dusty pillars to their explosive deaths that seed the galaxy with the elements for new worlds. And it has turned distant points of light into real places, sniffing the chemistry of alien skies and beginning the long search for habitable environments beyond our solar system. These are not incremental steps, they are leaps that have redrawn the map of our understanding. The James Webb Space Telescope is far more than a powerful instrument. It is the catalyst for a new golden age of astronomy, a moment where the questions are multiplying faster than the answers, and every new observation feels like turning a page in a thrilling, unfinished epic. This story belongs to everyone. You can be a part of it. Follow the mission. Seek out the raw, breathtaking images released by the Space Telescope Science Institute, and let your own eyes wander across galaxies that existed before our sun was born. Share that sense of wonder with someone else, because this is a human achievement, a testament to our stubborn curiosity and our desire to know our place in the cosmos. We are not just passive observers of this era, we are all witnesses. The history of the universe is being written in ancient light, and for the first time we are here to read it.